Hello everyone, it's November 30th. It's the last day of November. Look at this, a hot question. Let's see what we have. Maximum rectangle. I've done this before, but I completely forgot about this. I have no idea what this is. We gotta do more hot questions. I read a post yesterday. Somebody did 1,000 problems in 6 months. That was very impressive. A lot of questions every day. Okay, let's see. Back in 2019. Well, look at this. Start from 3 p.m. and last all the way to 7 p.m. Just trying, right? And just trying and trying. Okay. What is this? Given row by columns, binary matrix, filled with zeros and ones, find the largest rectangle containing only ones and return its area. It seems to be very benign, but usually a benign question can become tough. I mean, this one definitely, the tough part is going to be, I think it'll be timing out, right? Okay, so what was the idea? We need to find the maximum, okay? Wait, have we done this similar thing before? That I was using 2D prefix sum. Yeah, isn't this the same thing that we've done before, the 2D prefix sum? And the largest, oh, that one is the largest square. Hey, remember, that was the largest square. This is the largest rectangle, so it's slightly different. What was the method used eventually in that problem? I think it's binary search, if I remember it. I don't. Honestly, I don't remember how that one was done. Man, that's the problem. Like, you do it and you forget about it. But I do remember that I did it using prefix sum, but it was terrible. It was not good. And the actual solution is not prefix sum. It's binary search. How was the binary search work on that one? We have the length, and we're trying to find. I don't remember. I don't remember at all. Wait, what was it? Hey, what was it? Maximum. That's a maximum square, right? The maximum square. I'm trying to remember maximum square. I feel like it's binary search, but I'm not 100% sure. Man, I want to see, but I don't know which one. This is frustrating. I know I did it, but I don't remember. All right, so this is all the things I have. All right. Check valid, unique path, disappearing number, Hamming distance, single, non-duplicate. Let's build a tree, another tree. This is a DSU. I don't think that's a DSU, the one we solved. Largest component size, interval intersections, maximum subarray, search insert, product except self, all paths, no. Was it earlier this month? 130. Oh, this is a solving, no. Unique path, sum number, sum of left, arrange coin, single number, add number trees, find number value words, max profit, min star value, remove elements, daily temperature, combination iterator, largest divisible subset, concave. Oh, it's not here. So is it December? Oh, October. Flatten, longest dupe, orange rotten, threesome, sort color. No, no. Hold on, I want to see. I think I've done it. Oh, maybe it's one of these. I don't know. Hold on. So it's maximum rectangle. I think the one that I've done. Okay, so it's max, not rectangle, square. Maximum square. Oh, internet is back. Oh, yeah, I think it's down for a while. All right, now it's back. Okay, so this is what we have last time. No, not this one. 221, right? So I did a maximum square with 2D prefix, and then I use binary search. Yeah, that's what I did last time, which I think I can use exactly the same thing for this one as well. Yeah, I can use the exact same thing. Wait, what is this DP solution? The largest square filled with 1 that ends at ij. Right? So we say dpj if this is 1, then we can find the maximum that ending at that, which is the previous one and then plus 1. Okay, I think I know. So dp, right? dp basically saying terrible. All right, so are you saying at each position we can count? Oh, it's not the largest, it's square. Oh, that's why square is easier, because we have the square, right? And then we can say a square, but this one's not a square. So the largest rectangle, how about the largest rectangle we can achieve given from this? But what do you mean by largest rectangle, right? This is the rectangle, and this is also the rectangle, right? Which one should we pick? Let's say we pick the one with the largest area, right? With the largest area. But with the largest area, okay, how about we have a new one? I'll be saying, right, so the largest area from here, the largest area from here, and the largest area from here. Many sizes. Hold on, let me think. So for each position, I know like the largest, so like for this, the largest square or a rectangle will be this. Wait. Hold on. Let's say for this position, that's 1 on 1, right? That's it. So the length is 1, height is 1. It's a 0, we don't consider. It's a 1. It's also, and then we look to the left, that's nothing. And we look to this position, that's nothing. And we look to this position. Now this position is a 1, which give us 1 and 1, right? It's 1 and 1. It's 1, 1. So therefore we say at this position, the best will be, so we can go like the length, right? The width and the height. And the width will be determined by this position. and this position. And the height will be distributed by this position and this position. So we go with the width. And the width will be the minimum of this and this, which is 0 because it doesn't extend. Minimum of here is 1. So this one will be width was 0. Now width is 1, height is 2. Let's write it out. Right, let's write it out. Maybe we'll get more insight. Yeah, I feel like this is the same DP idea. And we have 1, 2, 3, 4. 1, 2, 1, 2, 3. Oh, 1, 2, 3. 1, 2, 3. 1, 2, 3. 4. I have 4. So we have first column is all 1, and then 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 0. Okay, so the first position, let's say we give it a 1, 1. And this position is going to be 1, 2. Right? The first one is the... Actually, let's just write in another one. 1, 2, 3, 1, 2, 3, 4. Right, 1, 1, 1, 2. And this position is the same. It's going to be 1, 3, and 1, 4. Right? Are you going to go rows or are you going to go column? Let's go rows. And this is just 0, 0, right? This is 0, 0. All the zeros are 0, 0. But these are easy to handle. All the zeros are 0, 0. Alright, this position. So this position, we're looking up, that's giving me 0. This is a 0, this is 0, so this one is a 1, 1. Right? Now this position, that's interesting. For left, nothing, this nothing, so this can be a 1, 2. This position go up is nothing. Right? So if go up is nothing, I already restricted myself. Right? I go up, that's nothing, I already restrict. So the height will definitely be 1. And then we go the width. So the width for this, I have 1. Right? And that's it. That's the only thing. Because this one, well, this one has 1, 2. It extends. Ooh. Yeah, and then this one gives us 1, 1. Therefore, the width is going to be 1. So adding 1 will be 2. So that will be 2, 1. Right? And this is the same. Up is nothing. This one is nothing. So here, this one extends to 2. Okay, so this extends to 2. And this does not extend. So anyway, so this one has no height. So the height is going to be 1. And the width going to be the same width as this. And this width is 2. So to me, it's going to be 3. I'm still trying to find a way to handle this. Okay, let's see this one. All right. So this one go up. So the height is going to be 1. And the width is going to be 2. Right? The width is going to be 2. So this one is going to be 2. Which is this. How? Come on, this one. This one, go height. Height, we get 2, because it extends to 2. And go width extends to 2 as well. So this one has height is 2, width is also 2. But this is a 0, right? So the diagonal is 0. Therefore, the maximum it can form. So what is the diagonal of 0? So diagonal limits that I cannot go more, right? So the height is limited by this, or height can only be 1, and the width can only be 1, but that's for square, but now it's rectangle, right? Which means this one has 2 possibilities. We can go, why do we have 2 possibilities? Because this is 0, 0, which means I cannot expand. If I cannot expand, Basically, we're trying to say how much expansion I can have. So I have the expansion on this one. I have the expansion on this one. So this gives me some hint, right? And I also have expansion on this one. And this one gives me expansion 0. And 0 does not expand, right? That means we cannot combining these two, right? We cannot combine these two. So we can only take one of this or one of this. And if this is something that I can combine, right, and then depending on the size of this, then I can extend this one as well. And if this one is bigger, then we'll be extending whatever is here. Okay. So we say because this one limits, so this one cannot expand. The maximum is going to be, the width is 1. Right? So I either follow this. So this one will be either 1, 3, or 3, 1. So I have 2 possibilities for this. And now look at this one. Right? So this one go up, I extend. Can I extend 1? Or here I can extend 3. The maximum I can extend 3. Alright? And yeah, so this we go extend up. This extend to the left. So that's 1 extension and 3 extension. Now we look at this one. So this one has 1 extension to the left and a 2 extension up. Right? How do we reconcile this? So I have 1 extension to the left. That means if I include this, right, if I include this, basically I'm trying to find the maximum rectangle, right? The maximum rectangle. So based on this, I have 1 extension to the left, right? And for this one, I have 2 extension. No, hold on, let me write it out. So for this one, I have 1 to the left and 2 go up. And for this position, I have 1 to the left. No, but this one is actually, oh, actually it has 2 to the left. This one has 2 to the left and 1 go up. Right? 2, wait, is that 1 to the left or 2 to the left? It's 2, right? This one is 2 to the left and 1 goes up. Okay, and this position I have 3 to the left, right, and 1 goes up. Do I need to consider the go up? I don't think I need to. So for these purposes, this should only consider go up, right? This determines how much up I can go. So this one just says I can go up for 1. And this says I can go left for 3, right? And then this one says, this one is more important. This one says I can go up for 2 and go left for 1. Because this only go left for 1, if I include this, which means I'm going to expand, right? If I include this, then I can only go left for 1, right? And go up for 1, right? I can only go left for 1 and go up for 1. Go up for 1 is restricted here, go left for 1 restricted by this. So this one will give me a 2, 2 and a size of 4. So that's one possibility, is including this one, which means I'm expanding, right? If I don't expand, I can also choose not expand, because if I expand beyond this, right, might as well expand as much as I can based on this. And if not, I need to expand either this way or this way. And go up. Hold on. Shouldn't we record all of them? The maximum I can go up, the maximum I can go left, and the maximum I can go the whole, like expanding. So for each one, I should record 2, 2, which is go a whole thing, and then go up, right? Go up is going to be, the width is 1, height is going to be 2, and then go left, width is going to be 4, height is going to be 1, right? And we can also record the current largest as 4. So okay, so for each position, I have 3 values. Okay, I have 3 values. And now looking at this one. So okay, so this one I have 3 values. Everybody should have 3 values, right? Everybody should have 3 values, which is vertical, horizontal, and diagonal. Okay, everybody has these 3: vertical, horizontal, and diagonal. So vertical is going to be 1, 2, and vertical will only record 1 value. Vertical only needs to record 1 value, which is just 2, right? Horizontal also 1 value, which is 4. Diagonal need to record 2 values, but we can probably, yeah, we can just do the 2 value, 2 and 2, right? So this one, right? So this one, I go vertical. Vertical tells me I have 1. So vertical, the previous vertical is going to say I go up, I can do 1. Horizontal, go left, I can go 4. And the diagonal, which we're looking at this one, right? Diagonal tells me that diagonal is this diagonal or this? No, this one has to go all 3 directions. So for diagonal wise, I'm gonna have vertical is 1, right? Horizontal is 2, and this one's diagonal is 1 on 1. It doesn't have diagonal. So 1 on 1 for the diagonal. So now looking at this one, right? If I go vertical, I can get 2. I go horizontal, I get 5, right? I go vertical is 2, I go horizontal is 5. If I go diagonal, and then look at the diagonal, look at this thing, look at this. This tells me that I can go up for 1, right? Up is 1, so I don't have 1 on the vertical, and we compare to the vertical 1, which means the vertical, the most I can go is 1, and horizontal. This one horizontal gives me 2. So this one has horizontal, so up and horizontal. Horizontal gives me 2. So what does that mean? Horizontal gives me 2, and we compare to the horizontal of actual I can get is 4. So horizontal I can get is 2. So for this position, right, I go up 1, I can go left 2, right? So that's one option, right? That's one option. If I want to extend, if I can extend here. What about but this will be extending here and here, right? Which helps me create another one. And we need to also see what about the diagonal this one can create. The diagonal this one can create is only 1 on 1 because this one diagonal wise is just by itself, right? And then diagonal by itself, if we use that, it's gonna only give us 1 on 1, or 2 by 2. But if we use the horizontal and a vertical, okay, horizontal and vertical. What if I have more horizontal here? If I have more horizontal, then supposedly we can get a bigger region, but now I need to consider its diagonal, right? I'll consider its diagonal. So how much this one can extend? So I know the extension to the left, I know the extension to the up, right? And I also want to know the extension diagonally, and diagonally, it depends on the extension of this one, this, and its diagonal. And its diagonal does not extend. But if it has a diagonal extend, then we can create a bigger one, right? And we can do like 2 rounds. Because its diagonal only go 1, 1, so which will give us only a 1 on 1. So it's 2 by 2, which is not good. But its extension can give us 2 by 1, right? So we can go 2 to this side, 1 by this side. So this one will give us 2 by 3, right? So 2 by 3. So go up. So vertical will be 2. So vertical I can go 2. Horizontal I can go 5. And diagonal I can go actually 3 by 2. 3 width and 2 height. And coming here, 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 and this one is easy to see. This one just have a horizontal, vertical, and the horizontal is nothing. So what do we say? Well, what we say is, let's try this one. All right. This one, horizontal. This one is 0, right? So horizontal, I'm limited. Horizontal, only can go 0. Vertical, I look at this one. This one's vertical is 2. So vertical, I can go 2, right? Diagonal. So diagonal for this one, horizontal. It cannot go. Horizontal is limited by this. So horizontal is limited. So horizontal, I can only go 0. Right? Horizontal, this way, I can only go 0. A vertical. Well, if horizontal is 0, if anything is 0, then that's it. Right? If anything is 0, if any direction is 0, then there's only one way. So this one, for this one, is just going to be vertical 3, horizontal 1, and diagonal going to be 1 on 1. Right? Because we have a 0 here. Okay, let's summarize. So what was the idea? The idea is for each one, I'll record 3 separate values. A vertical, how much you can extend vertically, how much you can extend horizontally, and how much you can extend diagonally. So we're kind of just expanding, right? So we have the maximum expansion you can have. So we have all 3 values. Then, for any given one, I can first get a vertical, get a horizontal. If any, and then when I check, right, if the vertical is a 0, then we're done. We can only extend horizontally. If horizontal is 0, we can only extend vertically. And if diagonal is a 0, then we can only extend horizontal and vertically. Right? So these are the easy checks. After these easy checks, now we have a situation where this position is not, we're looking at this one. So this is not 0, this is not 0, and this is not 0, right? So we have this, in that case, we're going to look at this one, right? We're going to look at this one, and we see its horizontal extension, right? So its horizontal extension, we can grab it, but is this going to be the optimal for the other things? I don't know if it's going to be optimal. say this one, I have a horizontal, a long horizontal, a long vertical. Yeah, we can actually a long vertical, but its diagonal is smaller, right? Let me draw it out. See if it's possible to build this case. So if I have, this is a 1, and I have this, and I have this, right? So the vertical, horizontal, all filled. In a diagonal, I have this, and I have this, but they only extend this way. So 1, 2, 3, 4, 5. Ooh, it's actually more. How about this? 1, 2, 3, 4. 4, 4 at 16. So this one will be bigger, right? So now I look at this one and go, this can give us 10, right? I can go vertical and give us another one. And I can go diagonal. So diagonal, this one diagonal will give us 3 and 3, right? So 3 and 3, and they are all within the vertical range. So this one can give us 4 and 4, right? So in this case, the maximum this can get is 4 and 4. But is this the best? Like, would I have something in the future? Would I have something in the future? Hmm. Like something in the future referring to this one. And this one will only refer to this part, right? And what if I have something like this, right? If I have something like this, again, all filled, but not filled here. These are not filled. So given this one, vertical, okay, I'll be restricted by the vertical. I am restricted by my vertical. And for this, I have a vertical, I have a horizontal, If I record, what I record is the largest rectangle, right? The largest rectangle. If it is the largest rectangle, it's the largest rectangle. But that's the thing. If I only record the largest rectangle, it could be that a subsequent check requires, like, the largest rectangle cannot give me the best option. That's what I'm afraid of, right? That's what I'm afraid of. Yeah, so this one I will say up extend this, left extend this, right? And then we look at diagonal. In a diagonal, I do have this, and I have this. Well, this don't work, so diagonal will give us just this thing and this thing, right? Now the diagonal, because I recorded the biggest, which is this. This is the biggest I record. And if I use that, we can say, okay, vertically we're going to extend it here, horizontally extend it. So I will only be able to extend to this thing. Yep, that's not right. That is not right. Maybe in this case we have to use prefix sum. How would you do prefix sum? Well, prefix sum, if I get prefix sum, I start from this position, right? Try to calculate what is the biggest, but how do you calculate? Oh, if it's a 0, we don't calculate. So we go for a 1, right? And how do you calculate if it's a, we have this value? Well, it can be anything, right? We have to find all possibilities. No, that's not going to work. All possibilities, that's not going to work. I feel like it's still a DP, but with a need to be smarter in DP. I mean, the left and right, the horizontal and the vertical definitely works because this gives me the range, right? Like this gives me the range. So once I have the range, so I know the maximum height I can reach and the maximum width I can reach. Now what? Now we just need to see if anything in the diagonal. So we go look for the diagonal and look for diagonal. Look for what? What am I looking for? Well, I am looking for the maximum reach. Okay. So what are you saying? I'm saying if I have at my position, right? I know the maximum reach I can have on the left. I know the maximum reach I can have go up, right? Then I look for this position, right? And this position will also have the maximum reach up and maximum reach to the left. And by its maximum reach up, I can compute this. The maximum reach to the left, I can compute this, all right? And okay, and after computation, I have a new restriction. So basically what I'm saying is, if I want to do 2 rows, right, then I'm restricted by how far this one can reach to the left. If I want to do 2 columns, I'm restricted to how far this one can reach to the top. But actually, it's this and this, right? Okay, so in this case, I will see this, and I will see this, right? Okay, so when this is done, now we keep going diagonally. So we keep going diagonally, and this diagonal will also, how many times it can go diagonal is limited by the reach on the vertical and the horizontal. So which will be mn and m, or the minimum m and n. Can we run this? 200 times 200 times 200. That's 3. That is 3. Yes, and if I go one more diagonal, then it has reach and a reach, right? So everyone has a reach. Why don't we, okay, everyone has a reach, right? So for any one, I can compute my reach. So I have a reach, vertical and horizontal, and my diagonal has a reach, and its diagonal has a reach. Every diagonal has a reach, right? So how do I compute? Basically, we're just computing the maximum area I can have based on all these reaches, right? And for my reach, I can set the limit on how much I can go vertically and horizontally, okay? So vertically, I can maximum go, let's say go 3, right? So I can only go 3. So I can look for 3. And what if like vertical I can go all the way up? I can go all the way up, then that depends on the diagonal one. And every time we go diagonal, we're updating, right? We're updating how much vertical and horizontal we can go. Yeah, but the worst case scenario will be very bad. The worst case scenario. And another thing is, I'm only doing this. I'm only recording 2 dimensions. Like this does not like the maximum. The problem is the maximum rectangle does not help compute the maximum rectangle on another position. Yeah, that is the issue. That's why it's hard. Yeah, I can try. Yeah, the thing is if everything is 1, then this method will be so slow. Right? It'll be so slow. How can I Yeah, I mean, if everything is filled, that is. Well, what if I also. There is a way, right? So, like, let's say for each position, I also keep the maximum it can extend to. I just keep that, right? Yeah, I do keep that. I keep 3 things: the horizontal reach, the vertical reach, and the maximum thing that I can have, right? And if the maximum is the same as its reach, then we know everything is included, right? If the maximum is not equal to the reach, which is possible, the maximum is not equal to the reach, then we know the reach is bigger. Yeah, the reach is bigger. Okay, well, that just means we can keep going, which is fine, right? If the maximum is not its reach, it's not like a 1 row reach, that means the maximum is not that. That means we can just keep moving forward, right? Keep moving forward until there will be a point where the maximum is the reach. Then that just means diagonally there's nothing more to go, right? And if the maximum is the entire thing, right? If the maximum is the entire thing, then we just keep going, right? If the maximum is the entire thing, the maximum is the entire thing. I have my reach, and I have the maximum it has. So based on this maximum, no, go back to the original problem. The maximum is this, right? We have to keep moving. Because based on the maximum, I can only get a small portion of it. Like, we can try the maximum, but we shall also hold on. If I can handle this, which means these are zeros, right? What if I record the maximum, not a single row, but multiple rows, and a maximum of multiple columns? Okay, now we're talking. Now we're talking. I think this is different. So not the maximum reach, so the maximum, how should I say it? Maximum reach, but how many, say, columns I can reach? Yes, how many columns I can reach. Because this will give me a very quick computation, which means for this thing, the maximum reach is this. So we find the maximum to the left, right? And how many rows I can sustain that. It could be just one, right? And that means, but still, I don't think. Yeah, we can keep multiple. So maximum to the left. Yes, that's the maximum I can go. Maximum to the left, multiple rows. Maximum to up, multiple rows, right? And maximum up, multiple rows. Maximum to the left, multiple rows. And as long as this is within the range, then I can compute the maximum to the left, maximum going up. Okay, and then I do the diagonal one, right? And then I do the diagonal one. So each position, I have the maximum reach to the left. I go as many rows up as possible. And I have a maximum reach up. I go as many columns as possible, right? So that is the value for each one. Now the new one comes in. I look to the left. I look up to know the maximum reach I can get, right? And then I look to the left. The left has the maximum reach to the left and how many rows I have. And if the rows is within the reach, then that's one possibility. Right, and that's gonna be my thing as well. And I will go up as well. How many we can go up, and how many columns, and that will compute and then that. So we have these two. Now once we have these two, it is also important to check the diagonal, right? When we check diagonal, how do we handle the diagonal? A diagonal will handle something that is just diagonal, right? The maximum we can reach diagonally. How about this thought? The maximum we can reach diagonally. Okay, so maximum we can reach diagonally. Because it's diagonal, it will be squares. That is square. The maximum we can reach diagonally is going to be a square. But no, wait, hold on. The maximum we can reach diagonally. Oh. Maximum we can reach diagonally. So why do we do this? It's possible that we're going to have 1 and a 1, right? And we have a big thing here. And then for that one is also Alright, look at this one, right? This one, let's say I have a giant thing. For this, it's just by itself. Right? For this is going to be maximum is this, right? And this maximum is going to be this. Oh, actually no, because horizontally, well, vertically, it's just 1. The maximum is this. And the maximum here is going to be this, because the maximum reaches to here, but it doesn't have this row. So I only have 1 row, right? So my 1 row is going to be this. But vertically the maximum reach is 1. So this is actually these 3, right? So for the maximum reach vertically, I can extend 3 columns. And 3 columns is less than this. So for this one, I can reach maximum for all 3 columns. So let's go up. All right, let's go up. Okay, so that's that. Do we need diagonal? Yeah, what if we have this one's giant here, right? And then we have a diagonal. And this will now record. Well, then we don't do diagonal, we do this. Right, we can do this vertical. How many we can reach? And horizontal, how many we can reach? This vertical reach is only this part, right? This horizontal reach is this part, vertical reach is this part. So for everything coming in, I can go horizontal reach. But what about the vertical reach of this? Vertical reach and horizontal reach. Hold on. Vertical reach, horizontal reach. So what? So when I come in, I'll check for vertical reach. So I check vertical reach of this thing, right? This thing's vertical reach. And I also check for its horizontal reach. Well, this thing's horizontal reach is just this. vertical reach, the horizontal reach. That tells me the maximum I can get from this position, right? I have a horizontal, how many I can go, how many columns, how many rows, and a vertical reach, same thing. So I have these two data. Now I have a new point coming in. And with this new point, I can have, how do I have the horizontal reach? That'll be the same. And my vertical reach. Well, my vertical reach will be the same as, no, it's not the same. It's not the same, because if I say vertical reach, it's going to just be a single line. It's just going to be a single line. And I'm missing a giant chunk. Yeah, I'm missing that chunk. I don't know. Alright, let's look for some help. Related topic, dynamic programming, monotonic stack, array, and the stack, maximum square, monotonic stack. No, how should I say it? I know that total area, right? So every position, I know the total area. Like this position, I know it's 1, 2, 3, 4, 5, 6, 7. It's gonna be 7, right? And this position give me 2. This position gave me 2. Well, actually, no 2. This position gave me 4. Nah, it doesn't work. No idea. All right, I'm calling quits. Let's take a look. Let's take a look. I know it's DP, but no, can't do it. No idea. Okay. Okay, what is this? So we have, it's vertical and horizontal. Exactly, that's how I thought. So if it's 0, we skip. If it's not 0, else it's going to be 1. Yeah, vertical is 1, horizontal is 1. We say if I larger than 0 and a matrix, so this is the up is 1. So I'm recording the how many vertical, how many horizontal. Okay, I get that. I was there. How do we find the maximum rectangle based on this? So the width going to be matrix item length. Okay, so I have the width, the maximum width. Height is 1. While height is smaller or equal to vertical. Yes, while height is smaller than this. Width equals max.min width and horizontal. So, so I do compute the maximum on the height, maximum on the width, right? And so the idea was right. It is go vertically. So we go this to check, and this to check. But what it says is we're gonna go up to check a new width. So we calculate the new one, and we go up, calculate a new one until. So I got it. It was the same idea, but I thought it's gonna take too long. I thought it was gonna take too long. Apparently not. But still, it's slightly different from what I thought. I was thinking about going diagonal, right? I was thinking I compute this, and go diagonal. So diagonal has this and this, and we can create a this, right, and a this. And then we go diagonal again. But yeah, it's easier just to go row by row. Anyway, it was bad. DP. Yeah, so what do we have? We have, I can follow the same thing, horizontal and then vertical, right? And they will only be, we do 2D on this? Yeah, it's gonna be complicated, so let's just do 2. Actually, I would like to have a DP equals to, it's actually gonna be 0, 0, 1, 1. No, 0, 0. 0 and 0, right? 0 and 0. For this in range, we go mn equals len matrix. Len matrix is 0, right? And then for range m, no, range, hold on. Range n, and this for this in range m, right? And then we're going to say for I in range m, for j in range m. So for each one, right? For each one, let's do fancy. From collections, import named tuple, right? And we just say point equals just a name, so element equals name the tuple element, and let's say vertical and horizontal, v and h, right? So here each one, right, is going to be element 0, 0, right? And I'm pretty sure I can do this times n, because they're this times n, right? And then for this, I'll say if I is larger than 0, so if I is 0, right, then we don't have to do the horizontal. So if I is larger than 0, I is larger than 0. Oh, I cannot do name the tuple. Okay, I can do name tuple. Then if I is larger than 0, then we can say if I is larger than 0, and right, if I is larger than 0 and hold on. First of all, if matrix ij is equal to 0, continue. Otherwise, if I is larger than 0, if I is larger than 0, then so the vertical, the horizontal is 1 and 1. Right. If I larger than 0, then v plus equal to dp I minus 1j, right? I minus 1j is going to be this dot vertical, right? And then if j is larger than 0, then h plus equal to dp I j minus 1 dot h. And once we're done, we can say dpij equals to element vertical and horizontal. So that is to fulfill the dp, and I'm going to compute the size. So I'm going to say res equals 0, and I'm going to say for, let's say k to l, right? So for k, let's say k is for k in range all the way to the height, right? All the way to the height, which in range h. Should be 1 height. If you 1 to h plus 1, right? So that's the height. Now, for every height, k, I can compute its width, right? So now I can say height, right? And a width is going to equal to the width equal to what? So height is 1, and the width is going to be the width of this, right? So width of this I have a width, so I have a width should be the maximum width. Maximum width is n, right? So width is equal to minimum width and this thing. So this is the dp, right? dp something j. So it's looking at the same j, but the height is different. The height is going to be the current height is I, right? Minus height plus 1. Because currently height is 1. 1, this will be 0, so I'm going to do this. And now height is going to be 2, so I minus 1. Yes, so width is going to equal to this, and the rest is going to equal to max res height times width, right? So go blah blah blah, and then we'll return res at the end. Yeah, no need to test. We know this one is a correct console. Use example. Let's run it. Oops. Oopsie daisy. This is dp dot vertical. Vertical height. Let's change it. I don't like that. That's just like vertical as a height. Let's go width and height. Right? And width and height. So if I larger than 0, vertical, this is going to be height. Equal to height. This is going to be width. Equal to width. And then it's going to be width and height. Width, height, height. Width with dp. This dot width. Okay. Try this. Index out of range. Mn equals. Oh, shoot. That's true. Let me say if not matrix. If not matrix. Wait. Yes, if not matrix. Right? Because it gotta have something. Have 0 rows or 0 columns. If 0 rows, you're gonna have a column. Right? This is 1 row. And I have no row or column, it's just gonna be this. So lamp matrix, if not matrix, then we just return 0. Yep. Let's try this. It's bad. So we did pass, but we checked this. Let's check the solution. That was close. That was close. And actually, we have to redo the whole thing. All right. Well, this one's pretty bad. And what about this super fast one? 4 milliseconds. '85. Well, this one's pretty bad. I knew it has to be. I knew it had to be dp, and I came close, and I also realized that for each dpij, right? Each dpij, I needed to record the max reach vertically and horizontally. But I did not. What I lacked was the realization of the procedure that computed the maximum area. Now I had an idea very close to the solution, but I dismissed it for being too slow. In reality, it does take OMN and I would say OMN and the minimum MN, right? I think that's what it is. Just take OMN, minimum MN to run for the current solution. I did check my solution 2 years ago. That was pretty bad. 460. So what was this fast solution? Is it the same? Each cell at J mark the left and right boundary that the cell is contained within, such that the bounded width can extend to a maximum height. Height the maximum continuous vertical stretch belongs to. Now we accumulate height. Don't understand. What was I writing? Hold on. For each cell at row J, okay, start J and end J. For each cell at row J, start J and end J mark the left and the right boundaries that the cell is contained within, such that the bounded width can extend to maximum height of the vertical stretch that the current cell is part of. Come again. Start J and end J mark the left and the right boundaries that the cell is contained within, such that the bounded width can extend to maximum height of the vertical stretch that the current cell is part of. Okay, so for the start, for each row, right? We're talking about for each row. So for each row, I have the left bound and the right bound. Okay, so each cell at row J, height J, record the height of the maximum continuous vertical stretch that the cell belongs to. So I have a height. Okay, call that height. For each column, right? So I think this is not J. For row, it should be for row I, right? For row I and height J, record the height of maximum continuous that the cell belongs to. Maximum continuous height, okay? And the height will be 0. And for each row, I am going to accumulate height. So we're going to go n. What is n? N is the number of columns, right? So for each column, if it's a 1, then height j, this column, plus plus, and I go to the next column, next column, next column. So I have all the columns will be 1, right? And then I'm going to record start for all j, for all columns. So if this is 1, if it's a 0, if it's this, or the previous one is 0, is going to be fresh start. Right? So what does this one record? The bound. Okay, that can be bound to fresh start. Else, the current cell start has to match the start of the previous row. Else, the start has to match the start of the previous row. So start j will equal to the maximum of start j and a fresh start. What does this mean? This just means the previous one is a 1. Right? If I look to the left as a 1, so I don't know where, so I'm going to have to ask my previous row, right? Previous row maximum reach to the left. Oh, because my left is a 1, but I need to know what my previous row is in the maximum reach. Not my current row's maximum reach. Okay, I asked the previous row's maximum, which is start j, yes. And the fresh start, we can get the larger of the two. And if it's a 0, then we're going to move the fresh start to j plus 1. And the start j is 0. Start j is 0. Why start j is 0? This is the left and right boundaries. Oh, but it doesn't matter because it's a 0, so it doesn't really matter, okay? Fresh end, so it's the same thing. Now, this is the thing. We need to compute the rectangle at each cell j given its height, okay? So for each cell, height j is the continuous height at j position, right? Because that's what we do, continuous height. If it's 0, I turn back to 0. Otherwise, row by row, I have the continuous height. Now, I have the left and right, the left boundary and the right boundary. So for the left boundary, I match the left boundary of the previous row, and the previous row is a match into its previous row. So this start j, so the left boundary, if it's not 0, right? If the left boundary is going to be matched for the entire column. Is that right? For the entire column. Because the left boundary, what I check for the previous row, right? And the previous row checked with the previous row. Okay, so the previous row checked with the previous row as well. So for the current position, for this position, right, I have a left boundary which extends all the way up until I cannot extend. Hold on, let me think. Until I cannot extend, I extend all the way up until I cannot extend. Now what is height? Height is the maximum I can extend at this position, the maximum I can extend. And the boundary, check my left, right? If the left is 0, then the boundary is just going to be the fresh start, right? Whatever the fresh start is, okay? So that would just be the of one column. If I have multiple columns, then I need to know the left boundary. And the left boundary, if I have something, then the left boundary will be something up, right? The left boundary. What if it's like this and this? at each cell j. Max at each cell j, given its height. Given its height, I think that is the key. So what we're computing is just the maximum rectangle at this height. And at my current j, if it's a single column, it's fine, because at my left and my right, then we're gonna have more. Because for this one, I will compute its maximum is going to be actually fresh start. Ah, I see. Wow, this is very good. This is very good, I see. I don't think I can figure this out myself. This is the faster solution, also from my previous attempt more than 2 years ago. So the idea is, for each row, we find the max vertical extension for each cell. Maximum vertical extension at each cell. Then we find the maximum, the max range to the left and right of the cell that also has the max vertical extension, have the same max vertical extension. And then we can compute this rectangle's area with easily. Right, we compute this rectangle with easily. So it's easy to find the max vertical extension. Actually, the extension reach. Right, max vertical reach. To find the max vertical reach at each cell. It is tricky to find the left and right boundaries, right, that also have the same max vertical reach. Now to do so, to find the boundaries, we use dp, right? So the key is to ask the left boundary of the cell above me, above the current cell, right? To ask the left boundary of the cell above the current cell, right? To ask that, and because the cell above me is, yes, this makes sense. So ask the left and right boundaries of the cell above the current cell. And since all these cells are aligned in one column, right, then by asking this left boundary of this, we can find, since all the cells, since we are asking the cells right above us, we are essentially computing the max left and right boundaries that support the max vertical reach. Right. If we find a zero, right? If we find a zero, then that zero would just be zero, right? That zero would just be a zero. If we go up, 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 and then we find a zero, because every time we go for up, and then when trying to find the maximum, and then the maximum start for zero is going to be zero, right? It's going to be zero. Yeah, we're gonna go all the way up. So every time I'm gonna find a maximum reach for this position, and eventually, let's say we're gonna hit a fresh start, right? And then we go down, and then if we go up again, that's a fresh start. And I will do the fresh start as well. Okay, then I will do the fresh start as well. And the fresh start will keep moving, right? The fresh start will keep moving because if we have a zero, the fresh start will move. Otherwise, the fresh start will get a front. And keep going, it will be the fresh start, fresh start, fresh start. So yes, we want to find the left bound. So these are all the left bound. And what we're asking is the previous row's left bound at the same position, the same column. What is your left bound, right? And if you are a zero, then your left bound will be zero. But that is, your left bound is going to be, actually your left bound is zero. So I'm taking the fresh start. Right? I'm just taking my fresh start, the current fresh start. So if the previous one is zero, I'm taking the fresh start. And that's the bound. Oh, this is very good. Support maximum. So this will run. So this runs in OMM. Okay, let's try to write it. Okay, so again, edge case. If not matrix, return 0. All right, now we're gonna have the left bound. We say left, right, and height. Right. Left is going to be, we're going to do mn equals len matrix and len matrix 0, right? So the left, what is left? Left, everyone is going to be n. 0 times n. So right is going to be n minus 1 times n. Right, so these are the right boundary, left boundary. Height is going to be 0 times n. And I want to say for I in range m, and the rest is 0. Right? Okay, this is for each row. Right now we're gonna do the left bound. I'll do the height. That's for j in range n. So do the height. Right? How do we do the height? We say if matrix ij is equal to 1, right? If it's 1, then we say height j plus equal to plus equal to what? Plus equal to height j, right? So plus equal to 1. Yeah, it's plus equal to 1. This is the height, right? And me, my height is 1. Yeah, plus equal to 1. Else we don't, if it's a 0, else if it's 0, then height j becomes 0 because height is the continuous vertical reach. If we hit a 0, then continuous vertical reach is ended. So that's the vertical. Now we're going to go to the horizontal. Before j in range n again, right? The left bound. So we say if left bound. So if j is larger than 0, right? If j is larger than 0 and matrix I j minus 1 left, right? And this one is equal to 1. So my left is a 1. Right? What if my left is 0? If my left is 0, I'm going to do the start. Right? So we're going to say start is equal to 0. So if my left is a 1, then it is possible. So I need to check previous ones. Is actually, wait, do I need to? Yes, I do. If my left is 1, then I can check my previous one. So the left j will equal to max, right? Left j. This is the previous row, right? That's the previous row. So this is the previous row's left range and the start. You can say current bound, right? We call it current bound. So we're going to just look for left bound of previous row. Of the cell above me. That's what this one is. Else, if my left is a 0 or j is equal to 0. If that is the case, it's a 0. Wait, it's actually no, there are two situations, right? So actually Aleph, this actually, let's do it this way. Right, I say if this is equal to 1, if my left is 1, okay, hold on. I have to be 1 for this to be considered. Okay, hold on. If matrix ij, myself, is equal to 0, myself is equal to 0, then current bound will equal to j plus 1. Because it's not me, it's a j plus 1. And left j equal to 0. If it's 0, we just say it's going to be 0 because we use max here. It'll be easier. Else, now my current is a 1, then we say if j is larger than 0, and this is 1, we're going to do this. Else, what's else? Else is either j equal to 0 or my left is is 0. So in that case, left j is simply, in that case, left j is just equal to current bound. Actually, no. Where is it? The current bound? Yes, in that case, left j is equal to current bound. Oh, actually, if j equal to 0, or this is equal to 1, then I must have experienced this already. So the left j is actually going to be equal to j, right? Which is the current bound. Which is fine. Yeah, let's just leave as this is. So this is for the left, and we'll do the same thing for the right. So current bound is n minus 1, and for j in range, n minus 1, right? Minus 1, minus 1. If it's 0, current bound is going to be j minus 1. Left, and this is going to be right, j equals n. Why don't you just say minus 1, right? To indicate. And everything shall be minus 1. So left bound is minus 1. Right bound, so this is the like edge. It's outside, right? Outside. So this is outside, indicating that it's not possible. So right j is equal to this. Else, if ij is 1, then we say if I is if j is smaller than n, and the matrix plus my right is a 1. So I'm going to go look up, right? Look for the right bound of the cell above me. So the right j above me is equal to, actually going to be minimum, by j and the current bound. Otherwise, if my right is a 0, then I'm going to equal to the current bound. Okay, so that's 2 rounds to get the left and right. Now we have the range, right? At each cell, I have its range that can support its vertical. So we can simply do it one more time for j in range n. We can compute the res equal to max res. So the entire square, rectangle, is going to be height j, right? And then we have the boundary, and the bound is going to be the right bound minus left bound plus 1. Right, and at the end, return res. Alright. Let's submit this. Oh, wrong button. No invalid syntax. Oh, no if. I do it again? Oh my god, yes, I did do it again. 2 times. Index out of range. J smaller m minus 1. There we go. This one must be faster. Yep, this one's faster. 228. 52. Okay, that will be it. Wow, pretty bad. We didn't do it today. This is a tough question. I'm going to put that as my nightmare. This is a nightmare. All right. I'll see you guys tomorrow. Adios.